我今天讲一下这个，我现在正在写一个 review article，就关于农历气象60年，近看60年以后呢，我们邀请了一批人回顾过去60年在与农历气象相关领域有关的地方，过去60年的进展。我呢就是自己自己的就是想写这方面，就是关于能量、水、碳、核的过去60年的一个进展。如果我们来说，就是说，我们问一个问题，就是说，过去60年，从 fundamental progress 在 energy water cycle、carbon cycle 或者 carboning 这个3个 cycle 里，我们有哪些对后面的研究过去60年有很多重要的影响的话，我个人这是我个人一个 list， 不一定完全正确啊。我觉得在 energy and water cycle 最早的是 Pellman equation， 然后是 Monin-Oblakov similarity theory， 有 Boutic curve、Pellman-Montis equation、Price-Taylor equation， 那么这5个主要是关于 ET 以及现代微气象学一些基础东西。Carbon cycle 当然就包括了这个我们发现了碳3、碳4 carbon cycle， 在1950年或1966年。我觉得除了这个以外，一直对我们这几年60年有影响的是卡文的发款，他们的 optimization theory 以及发款的 photosynthesis model。的 coupling， 关于 water carbon coupling， 我们谈到 water carbon coupling 一个最常用的 index 吧，或者一种 measure， 就是这种 water use efficiency。最主要我觉得最前沿的工作是1965年，比尔辉整跟 Ralph Slatcher 以及 Graham Farquhar 的这个 theory， 关于 water use efficiency 怎么跟 carbon isotopes 联系起来的。我们现在都从现在来讲，如果我们来讲呢，就是现在我们回顾，就是说关于 model carbon water cycle， 我们估计至少有上千个 ，if not 10,000 这种 models。有这种 coupled energy water carbon cycle，even neutron cycle， 已经在most OSIS models， 这些 model 用来 projecting future climate and environmental change。但是最主要一点就是说，很多这种 fundamental progress underpinning of the models were developed more than 40 years ago。那我们就问一个问题 ：Are we really making progress？ 我们谈到 coupled energy, water and carbon cycle。那么 energy and water cycle，this is well understood. The physics of latent heat transfer was well understood in 1762. It's more than 500 years ago. And we talk about direct observation of water and carbon coupling at a leaf scale was made possible with the invention of leaf gas exchange， 在1964年、63年、64年。然后呢，在同样的时候 ，including surface conductance into Pellman-Montis equation in 1965, 63, 64, really started a new era of study of water-carbon coupling。OK， 这个是在1965年，比尔辉整跟 Ralph Slatcher， 在澳大利亚国立大学他们做的工作，在国立大学做的工作，他们发表农历气象的。他们当时提出一个概念，就是说 E over A， 那么 E over A 就是我们的 reciprocal of water use efficiency， 在 leaf scale 上，它就等于这个公式，基本上也就是说，这个 E over A is really proportional to the gradient ratio of water vapor and CO2, and also the ratio of the resistance of 这是 carbon dioxide resistance pathway， 这是 water resistance pathway。OK， 然后他就这个理论公式，然后呢，通过实验，他们也印证了他们这个公式计算的准确性。 同时他们发现这是在两个不同的植物上做的一些实验，然后他们也 predict， 就是说这个公式最后you can predict E of A is proportional to VPD, and this is true for wheat, rye, potato, oats, peas, barley, and corn. So rough selection 估计现在年轻人，这是00后肯定不太清楚。这个人是一个非常有名的澳大利亚的科学家，他的有一本书叫《Plant-Water Relations》，其中 laid the foundation of water potential， using thermodynamics。所以你要现在把这本书拿来读的话，你可能感到还是很 ，it's not really that old, still very modern, but it was published in 1967。那么在同样时候，John Monteith，他是当时跟彭曼一起工作的 Rosmstead。彭曼呢，当时为了计算这个 evaporation， 因为我们当时就是说彭曼是一个physicist， 这个物理学家，他就发现了这个公式，就是说 latent heat is a function of latent radiation, VPD, wind speed, and temperature. Okay. Monteith really modified but that equation only applies to wet soil or water bodies, lake is really saturated surface. If you want to apply the equation, try to calculate unsaturated surface, such as vegetative surface or unsaturated soil, Monteith introduced the RV, which is vegetation resistance. RH is heat, resistance for heat. So he stated the parameters RH, parameters, not variables, RH, RV allow equations for heat and water vapor flux derived from a single leaf to be applied to plant community. And he published his work in 1963. So when his work was going, and he was invited by then the chief of plant industry in CSIRO, Lloyd Evans, in 1962 to Canberra to give a talk, and had a symposium, and also a number of other top really heavies at that time invited to Canberra to the workshop. This including Rich Taylor from CSO, Bill Swinbank from CSO, Chapman Tanner from America, and John Phillip. And Tanner then all of those guys are very critical of Monteith's work. And C.B. Tanner said in his paper, so the whole papers at the symposium were published as a book, published by Cambridge University Press in 1963. And C.B. Tanner has a chapter, and he wrote, the derivation of IS or RV is invalid when the source and sinks of heat, water vapor, and momentum was set at different levels of canopy. So you can't apply a resistance for heat for water vapor or resistance for momentum for heat. So you really can't exchange those things. John Phillip is probably the most vocal person critical of Monteith's work. John Phillip is a guy, he's really a genius guy. He went to university at the age of 13 and got his PhD when he was 17 or 18, 16 years old. He's an accomplished poet. He's an accomplished architect. He's also, he published, I think, 3 or 4 papers for his PhD at age before 20, and got a Doctor of Science from Melbourne University, and all those papers become a citation classic in soil physics. Okay, so it's a very smart guy. So he was very critical of Monteith's work. He said Monteith's work is superficially mathematical physical, but which contains loose thinking and non-rigorous calculation uncoordinated physical measurements in the field and an overinflated claim. And it's an artifact of somehow unrealistic analysis, and its physiological significance is questionable. Okay. So since then, and I think now looking back, and I think some of the criticism have some, they are really smart people, has some values, has some point. Whether it's true or being too harsh, we can debate about this. I think since that was in 1960s, and then 70s, 80s, 90s, I would say the golden era of micrometeorology and ecophysiology and canopy process. At that time, I think there are a number of major advances being made. One is by A.S. Tam from Edinburgh University. He first derived the profile for heat and momentum transfer in vegetation canopy in 1972. And Tom Demmit and Frank Bradley from CSIRO, they first discovered by measurements of counter gradient, which means the flux actually flow normally from high concentration to low concentration, or from high temperature to low temperature, but in cross canopy, it's not. It's actually somehow can observe flow from low to high concentrations. Okay, that's what we observed in 1985. And that was explained by a theory published by Michael Ropak, a lot of CSO scientists. He can explain the counter gradient flow by using the near field and far field theory for canopy turbulence. And I think the other important contribution made by Paul Jarvis and Keith McLaughton about vegetation atmosphere decoupling. So, which means you're scanning from leaf stomatal conductance to canopy to regional scale, and actually change the sensitivity of regional of evapotranspiration to surface properties. Okay, as a result, nowadays, so the equation here, this is really the original formula published by Montes. Nowadays, if we write a Pema-Montes equation, this is the probably more physically accurate way of writing Pema-Montes equation. It involves changing of the lateral radiation into isothermal lateral radiation, introduce of radiative conductance, also counting for the different height for sink height, source and sink height for water vapor and heat. Okay, this is why there is a ratio here. Okay, I think it's why is the ecosystem evapotranspiration different sensitivity to BPD, to environmental variables varies with scale. We know at a leaf scale, transpiration is nearly proportional to leaf conductance. Okay, it's always when you increase the leaf conductance, you increase transpiration. At a canopy scale, particularly at regional scale, when you involve a boundary layer, that is a different story. So let's say, if you in the morning when you have a growing boundary layer, okay, with surface heating goes up and the boundary layer goes up, the boundary will encroach the air above, which is much drier than the air in the boundary layer. So there is a reduced humidity, therefore increased VPD. The increased VPD would therefore increase the surface conductance or stomatal resistance, or reduce stomatal conductance, which would therefore drive the reduce the stomatal conductance, and therefore reduce transpiration. Okay, so this is one kind of inference of through the boundary layer. Also, by increase the drying, it will also increase the canopy temperature. It will also increase the leaf surface VPD, which tends to increase the transpiration because the gradient is bigger. So therefore, increase transpiration, therefore partly counteracts the effects of drying on stomatal conductance. Okay, so there is various feedbacks. So at the regional scale, of course, when you involve the planetary and convective boundary layer, and therefore the evaporation at the regional scale at a point also depends on the regional air circulation, mesoscale circulation, and how the air is mixed with the neighboring cell. So that's this scanning of evapotranspiration from leaf to regional scale properties were explained by the decoupling factor, which I think I'll go to slides here. Sorry, I should. Okay. Not this one. Okay, so basically when you can write the ET as a formula of the in terms of decoupling factor omega, and weighted by is really if actual evapotranspiration is a function of equilibrium evapotranspiration and imposed evapotranspiration, and weighted by the decoupling factor omega. And therefore, if we write in this equation, this formula, the relative sensitivity of E to stomatal conductance is proportional 1 minus omega. And omega tends to be a much smaller, the decoupling factor tends to be a much smaller value for forest, and the crop tends to have a much larger value. Therefore, forest canopy evapotranspiration is much more sensitive to surface conductance than crop canopy, because forest is well coupled to the atmosphere. Okay, just make its point. Okay, let's go back. So the other things we really how the leaf scale stomaticness is related to canopy conductance, surface conductance. That really that kind of relationship has been worked out by a number of people. I think Michael Ropack's paper in 1991, 1995 paper in agriculture, forest meteorology, Keith McNaughton paper in 1994 in plant cell environment. Basically, in summary, what the key message is, surface conductance, which is 1 over RV in PM equation, is not a simply integral of leaf stomatic conductance. If an average scheme to a multiple from leaf to canopy. This is point number 1. Point number 2, the averaging, how the average scheme for water vapor. So the relationship between the surface conductance for water vapor and the leaf stomatic for water vapor is different for CO2 or for surface temperature. Depends on the flux type. Okay, exactly. You really go back to read those papers, 3 papers, so you understand why they're different and how the scaling varies. Okay. So when John Philip was really critical of Montiel's work, he proposed the idea of soil plant atmosphere continuum called SPAC. So he said the SPAC should be like something like this. It has, because John Philip is a physicist, so he said, oh, it's really like setting up, basically it has a boundary conditions, energy source with the initial conditions at a different, atmosphere, vegetation, soil, waters, different layers. And there is transfer equations, possibly second order partial differential equations for energy and water. And in those equations, you would have conductivity, diffusivity, and other coefficients. And finally, the whole transport of energy and water depends on the geometry. What he means geometry means the roots. How much roots, what sort of roots you get, how deep the roots in the soil is. And then he said, the the problem is too complicated. But remember, John Phillips is a very good applied mathematician. He said the problem is complicated. Simplification are necessary that include semi-isothermal, quasi-stationary, simplified geometry. And I'll come back to these points, later. Okay. So after John Phillips published his spec paper, so Ying-Ping, another well-known Australian scientist, in 1965, he published the SPAC model, basically on theory. At those days, there is no validation required. You construct a number of equations, you write a paper, do some simulations, here you publish a paper. But it was really the first person put a really mathematically formulated John Phillips' idea and did the simulation. And he, in 1968, he then extended the work to include mass, heat, and momentum transfer between the vegetation canopy and atmosphere. The 65, 68. And this is the same Cowan who supervised Grant Farquhar as Ying-Ping is Grant Farquhar's PhD advisor. Okay. So in the meantime, in the 1970s and 80s, and there is a lot of crop modeling going on. This is kind of really interesting. The crop modelers, they can do model crop yield without a modeling photosynthesis. So the way to do it is that, well, the yield is equal to water use efficiency times transpiration, okay? And the water use efficiency is equal to K is a constant divided by VPD, so times T. So that, remember, the first term is come from Beer-Huizen and Sledger theory. And the ET equal T transpiration plus evaporation. And the evaporation of soil basically is based on the John Phillips' idea, the infiltration theory. Okay, that is the one paper he published from his PhD thesis. Okay, so it's a proportional. So what he's saying, the soil evaporation will decline between two rainfall events as a function of square roots of time. Okay. And then you got another equations, the ET and the maximum potential ET is a function of soil moisture and vegetation properties. And coupled with a soil water transport in soil, you can solve these equations to work out the T and ET, and therefore by multiply by K divided by D, you can calculate dry matter productions. And that is the way they do crop modeling without carbon cycle. Okay. And then 1988. So and then 1980s, I think 90s, I just finished my PhD, and then the global change become very hot topic. And there was people who work on global climate models and try to improve the representation of land surface. So the first generation of land surface models in the global climate models basically has 15 centimeter global uniform soils, okay, globally everywhere. So the vegetation is everywhere the same. I think maybe with decided one or two different height type. So it's a very simple representation of surface vegetation. And that was criticized by Robert Dixon and Seller said, well, those models is totally inadequate for quantify the effects of land use change or deforestation on climate. It's just totally inadequate. So at that time, then Pierre Seller and Bob Dixon, and then developed the second or third generation of global land surface models. The key difference between the first and the third generation of land surface models is introduction of Pemman-Montis equation into the land surface model. And even in third or fourth generation of land surface model, like CM4 or 3, also including the photosynthesis model of Farquhar's photosynthesis model, okay, and Bohr and Barry's stomatal model. This is later on story. So I think this is a very nice study with the SIP model, Pearcella's model. SIP is boss model. So what they have done, I think this is the earliest more studies quantify the physiological warming I can find in the literature. So what they are saying, when you increase CO2, yes, you increase the radiative forcing, but you also reduce stomatal conductance. When you reduce stomatal conductance, you actually increase surface heating. Okay, therefore you also have a larger increase of surface temperature. That's called physiological warming. That is the first paper quantifies the physiological warming. Okay, that's the simulation on the right. I'm not going to go through the details. What in terms of water carbon cycle coupling, there was is very interesting. So what they have done, they did the simulation for, they call it control, which is a 320 ppm CO2 concentration at the time. So they run the model with an undersurface with Lassus climate model with a CO2 concentration of 320, they could control, and they compute GPP ET, all right? And then what they have done, they said, well, when you double CO2, you would increase the radiative forcing, therefore increase surface temperature. So with the increased temperature, you increase VPD, therefore you reduce, you increase the ET slightly, okay? Therefore, you would actually, without much impact on the GPP, therefore you will actually reduce water use efficiency in some way. And then in the third simulation, they said, well, then if you count for the higher CO2 would actually stimulate photosynthesis, okay? Just stimulate photosynthesis. Therefore, you would also increase GPP. Therefore, you would also increase water efficiency. And finally, the increased CO2 would also reduce stomatal conductance, therefore reduce ET and reduce photosynthesis that would reduce the water use efficiency. So this is kind of first set of simulations being done with a global model at a global scale by Pearcella, and paper was published in Science in 1999. I think this is the first studies. And data has been regenerated down by modern models again and again. I don't think the results is much different. The broadly very similar. So at that time, it's about year 2000. I remember Ines Fang visited CSIRO at Aspen, my institute, and they had a meeting. And they got very excited. Ines Fang is one of the pioneer in global carbon cycle or greenhouse gas modeling. So she's really the leader. So I think if I may be wrong, I'm pretty sure Pierre Friedensteen and Jim Ransom both did a postdoc with Ines Fang in Berkeley, right? At that time, there are two groups. At that time, when we're doing climate model, climate projection, we always do, they call it 1 CO2, which is water 350 ppm, and then doubling CO2, or using the prescribed time vary atmospheric cycle driving the climate model to predicting climate. This is unsatisfactory because we know atmospheric CO2 concentration is a function of the carbon emission as well as the climate itself. So it's not really, you can't prescribe concentrations because it's not independent of climate. So what you do need is nowadays we call it a system model, be able to predict atmospheric CO2 concentration and therefore predicting climate. And two groups did this kind of simulations in about year 2000. They published that work. One is the UK Met Office, published by Peter Cox in Nature. The second group is by French group, published by Pierre Friedensteen in GRL in 2001. So I don't have the original figure. Basically, this is similar to the results here. So the black one means the land carbon uptake evolution over time by the Met Office. So initially it's a carbon sink until about the year 2040 and then become a carbon source by year 2100. You can methods of office model. The reason for the strong source is the collapse of Amazon forest. Okay, and the IPSL model, on the other hand, would predict somewhere here. I think it's somewhere green line here. Would predict the land base will continue as carbon sink. So we really get a very two different contrast response. And it is from them proposed we should do the C-quality flying leap for carbon simulation. They call it C4MIP simulations. So now we have, I think the last IPCC will probably have more than 14 or 15 of these models doing this kind of simulations called fully coupled energy, water, carbon, or nutrients simulations. So I want you to go back to say the spark idea. The spark idea, remember this is in Cowan's. I don't no point to go through the details. What is loss of resistance is a network of resistance to representing the resistance of the heat, momentum, water movement from across the whole spark system. So in the case of water, so it's really transporting of water from the soil to leaf to atmosphere. So along the way, there are various resistances. That's in Calvin theory. And then if you go to Kennedy's paper in 2019, CM5, they are similar, really, they are similar. You can also see the footprints of resistance in soil, hydraulic conductance resistance for sounding leaf or shaded leaf. So, it's I think we're going back to the idea what John Philip proposed, but the difference is we actually I also use a quasi-static stationary theory approximation. So I think we adopted some of the ideas by Philip. Of course, we have a different stomatal model. We have different photosynthesis model, we have different transpiration model. Some of the theory has changed, but the idea is really similar to what John Philip proposed in 1963, okay, 65. So nowadays, I think we have tools, a range of tools for studying coupled water and carbon cycle. We have the land surface models, ocean models, whether remote sensing-based models or biophysical models, observation-based data analysis, including machine learning. I think that over the last, as I said, if you ask if let's say in 50 years time, 100 years time, I think if you talk about the most remarkable work in global change, you ask people in 100 years time, they said, well, I can remember the David Kenyon's CO2 curve. Okay, this is the most impressive is observation-based records of global change. I think the second one, I would, because I'm in the assistant modeling group, I would still remember the simulation done by UK Met Office by, the attribution the global warming we already experienced can only be simulated by global models by including CO2 radiative forcing. So I think that to me, there are the two things. The third thing is the ozone hole story. So the other things I think they are largely based on the observational evidence. We'll really go to the history book as the key advance, I think. So I think this is another really nice piece of study by really look at the global atmospherical CO2 growth rate in gigatons per year, and strongly correlated with the total column soil water. So when the water is small, soil water is less, the growth rate of atmospheric will be higher. So which means the uptake by land and ocean will be weaker. When the soil water is high, the soil is moist, the uptake by land base will increase, then the growth rate of atmosphere CO2 will be slower. I think to me, this is the really beautiful evidence to show the strong coupling between the water and the carbon cycle at a global scale. And nowadays, I said, we have a range of approach, hundreds of models for doing the global scale carbon cycle, water cycle. When we do get a reasonable agreement in terms of GPP latitudinal pattern between the machine learning, process-based model, or inversion, they are all agree. GPP is the highest in the tropics and the lowest in the desert. About 25 degrees here is large desert area, and also desert area there and there. So it's a very consistent latitudinal pattern. But when you look at the interannual variabilities or annual variations of GPP, there are a huge discrepancy. In general, the GPP simulated by land surface model is greater than machine learning, and machine learning is greater than light use efficiency kind of models. And the trend, not only the interannual variability, the trend also has similar. The light use efficient model has the lowest trend, and land surface model has the highest trend. And the reason being, I think in some way, light use efficient model, in some way, that are not really fully counted for increase in light use CO2 polarization effects. This is one of other story. And this is the maybe contribute to the difference between the light use efficient model and land surface models. But there is huge uncertainties. And if we go to ET, again, we see very much similar patterns, spatial patterns between the light use, remote sensing, machine learning, and the land surface models. The highest in the Amazon. And if you look at the latitudinal pattern, there was a similar, again, the difference of ET is largest among different approach in the tropics, was the absolute ET was large. And there was a simulate very different trends. So they will simulate the ET increase over time from 1982 to 2011, but the trends is different between the land surface model simulated much weaker trends than the machine learning or other than the biophysical model, remote sensing based product. And then you look at water use efficiency. The global scale, this is like a global scale. The water use efficiency, because some of the light use efficiency doesn't simulate, only simulate carbon, doesn't simulate water, or some of the water ET model doesn't simulate the carbon cycle. But the land surface model does both. So so then if we compare different land surface models, simulate the global ecosystem water use efficiency, how they change over time, you can see they will increase over time. And the issue there is the absolute value of water use efficiency varies from 1.3 to 2.2, the D for limited by factor of 2, okay? And this is the global scale. Also, there is a paper, I think, I think this is Trevor Killen's paper based on 80 flux tower data. He estimated the trend of global scale water use efficiency is about 40 milligrams carbon per kilogram of water per year. And a subsequent estimate vary from, less than 1 to 20. So right now we have only the absolute value of total global scale water use efficiency differ by factor of 2. Also the trend differs by also at least 1 order of magnitude. It's huge. And this is a very nice paper by Fei Li and Professor Ji Guan Chen in Science last month. I think this is a very nice paper. They showed the global scale water use efficiency increased up to year 2000 and then become constant. The reason being constant because of the increasing VPD at the global scale. Okay, so what really in terms we tend towards use Perman-Matisse equation, inverting the Perman-Matisse equation, and say this should be the larger stomatal response. So this is not paper published in agricultural forest meteorology, and they using this model. They call it I call it surface conductance, or GS, is a function of VPD and the GPP and the CO2 concentration. It's kind of a formula, the unified formula between the Lowndes model and Belinda's model. I think they, by using that formula, they calibrate against the 77 flux tower site, and they get a value of M between 0.4 and 1. So if you take the Medlin's model, the exponent should be half. If you take a Lowndes model, it should be 1. So it's not really half and a 1. So it's somewhere between for 77 sites. And this paper they concluded that, well, the reason is not half or 1 because stomatal conductance is not operating at optimal level. This is their interpretation. My interpretation, I think that is the issue. Could it be possibly complicated by the scaling? The scaling between the leaf and the canopy scale. So it's not a simply, in other words, the GS is not a simply integration of the leaf stomatal conductance. It involves other things, And the other recent work is from Beijing Normal University to really show very clearly by analyzing the remote sensing data that identified the GPP and VPD relationship is not always negative, okay? It could be positive. This is a slope, okay? The vertical axis y-axis is slope. The slope is positive when the mean growing season VPD is less than 4 hectopascal, so 0.4 kilopascal is positive. Once it's over 4 hectopascal, the slope then becomes negative. And that the positive path is something we cannot predict by our current models. Okay, this is one study, look at the growing season. This second study, look at the diurnal pattern of sensitivity of SIF, which is a proxy for GPP to VPD. They showed in the morning, the GPP to VPD is positive. In the afternoon, is negative. Positive is red, the blue one is negative is blue. So positive in the morning, negative in the afternoon. And this, again, this kind of phenomenon is cannot be explained by our current models. So we really have lots of issues. So a global scale with lack of sufficient data constrain global simulations. So for example, there is no globally observed ET available. So all of the ET products are generated by models. And the problem, one of the uncertainty of those ET product is with the precipitation data using those ET product also has a very large uncertainties. And we don't have a lack of systematic benchmarking calibration, and we have undersampling regions, a missing process with scaling issues still remain. So where do we go from here? I think machine learning will be the way to go. And I think the second one is the lowcast and forecast with data simulation will be very important. And I think it's a key advance in global science is wide response to some key process, various scale, time and space, and maybe we need some new theory. Okay. So finally, I said that, the question, are we really making progress? I say yes, we have more observations than ever before, more models than ever before. We also have more evidence of a strong coupling of water the cycles at a regional and global scale. And we have nearly completed SPAC, also outlined by John Philip in 1966, with a few twists and turns. including the later development of plant hydraulics. That has been implemented into a number of global land surface models. So John Philip, in his 1966 paper, I think it's a very long, interesting paper to read. He said our model is useful, often indispensable framework on which to organize our knowledge. The quantitative consequence of any model can be no more reliable than the prior agreement between the assumption of models and the known facts about the real phenomenon. Okay, thank you.